Welcome, fellow sciencers. I am Aaron Freeman, co-host of the Chicago Brain Buddies, along with Professor Peggy Mason, and we are here joined by Dr. Maria Weber to talk about quantum neurobiology, planetary magnetism, and all kinds of fun stuff. Welcome! All right.
So why are we doing this?
Yes.
You expect me to remember? I think it's because I saw that article on mallards, right?
Yes, that's what you told me.
Okay, so we see this article on mallards, and you know, okay, one of those plaguing questions is how all of these water birds land without running into each other, right? They're all landing. First of all, they're going in the right direction, and second of all, they're going at the right inclination. And how does that happen? And then somebody figured out that, in fact, they all land, different water bird species land at a different relationship to magnetic north. And this is another one of those functions that we see commonly in birds, but also in other taxa, where they are acting in a way that makes it obvious to us that they can sense magnetic north. And then we went down a rabbit hole.
That's it.
And I actually blame you for the rabbit hole.
I blame you totally for the rabbit hole.
No.
I was minding my own business, not even thinking about this mess.
Yeah. But I got the biology part, but you went down the quantum rabbit hole.
We'll get to the quantum stuff,
Okay.
which is so weird. But speaking of magnetic north, we have here someone who actually knows quite a bit about magnetic north.
Unlike us.
That's right, Dr. Maria Weber. Tell us about it.
Okay, well, when we talk about magnetic fields, well, first of all, the Earth has a large-scale magnetic field, and so do stars. I study, specifically on my day-to-day job, the magnetic field of the sun, and it turns out that the processes that create the sun's magnetic field are not too terribly different from the processes that create the Earth's magnetic field. So maybe I'll get more to that.
Does the sun have iron in it?
No, the sun is made only of hot gas, mostly hydrogen and helium. But it is so hot that some of the electrons can separate from the nucleus of the atom, and that allows these electrons to move freely around. And when you have a bunch of sloshing, spinning, freely moving electrons, you get a current, electricity. And as a byproduct, you get very strong magnetic fields. So that's how it works in the sun. In the Earth is like, the Earth's interior is like a rocky, molten, liquidy thing. And so it's not hot gas, but it's the motion of this molten liquid that when you stir it up, whenever you rotate it, whenever it moves because it's hot and convecting, it can also generate an electric current, which thereby generates a large-scale magnetic field.
So
are we sucking in all the metal in the solar system?
No. The magnetic field isn't that strong. It's not like, a crazy magnet. It is magnetic, but it's not strong enough to suck in other magnetic-y things.
So one of the reasons why I wanted to talk about the magnetic north before we got into the biology part was because there's a news story in Twitterland, which I bizarrely participate in. Who would have thought? But that it's been traveling. We're having a little seesaw with Russia, back and forth, and
Magnetic
so,
north, you mean?
Yeah, magnetic north is moving.
What?
It's on the move.
Everybody wants to get
And
away
so, it's actually a few feet.
Yeah,
is it a few feet a year?
I
It's a few
don't
inches.
know. I
It's
don't
a
know
few
the exact
somethings
rate.
a year. It's quite a bit. So, do the animals actually have to accommodate for this change?
I mean, yeah, I guess they would have to, right? So this image that I have behind me here is a picture that shows how the Earth's magnetic north has been moving over time, and my eyeballs aren't good enough to really see.
Can you
but,
try and focus that lens?
but in general, the magnetic north has been sort of meandering around from somewhere over here into now it's somewhere right here. So that's the North geomagnetic North Pole.
Magnetic north is not at the North Pole?
Sorry?
Magnetic north is not at
It
the
is
North Pole?
not. No, magnetic north moves around. And you can see the trajectory that it's taking here. So they expect in 2020 it's going to be somewhere here. About right now it's somewhere here. But in 1994 it was right there. So this is above Canada. Yeah, so it does move around.
So why is it close to but not on the North Pole?
Oh, okay. Well, the magnetic field isn't really bound by the what we call the geographic North Pole. The large-scale magnetic field that we see, what we classify as magnetic north, is created by the motion of that liquid metal inside the Earth's interior. And different parts of it move at different speeds at different times, and the motion of that over time is what can shift the large-scale magnetic North Pole over time. So it's an effect of the way that the molten liquid inside the Earth's interior is moving around. It's a process of what we call a dynamo, and a dynamo is any process that creates magnetic fields within planetary bodies.
So is the idea, so the other thing that was surprising to me is that South Pole, very boring, sits in one place, doesn't move.
Well, it does move.
Is that because the molten stuff is not so close to the surface?
No, it's not necessarily about depth. It's just about the way in which it moves. If it's faster or slower, or they can make little vortices, like little swirling eddies. You know, when you play in a pool and you move around, you see little swirling bits. Different things like that can pop up in different places in the interior of the Earth and the interior of the Sun, and that can affect the magnetic field overall. So it's really just the way that the liquid inside the Earth is choosing to move. Yeah.
So why do we think that birds are using magnetic north?
We think this for a variety of reasons. One is that if you impose a really strong magnetic field on animals, it will shift their behavior. So, for example, if you take salmon, they will swim up east-west. If you shift their magnetic field 90 degrees, they go north-south.
You know, I don't know. You know what the cone that they use to tell that birds are traveling in magnetic north, sensing it? There's this really wonderful contraption. It's a metal box, and then there's a cone. And at the bottom of the cone is a little inkwell, a bunch of dye, and they put a magnet at one end of the box, and they see if the bird tries to fly in that direction, and the path that the bird takes is revealed by the dye markings on the cone. It's like an old experiment. It's old but
I love
clever
those kind of clever things.
Yeah. Old but clever nonetheless.
Well, I mean,
yes.
and then
So,
in the terms of, say, the mallard study, what they did was they studied the angle of landing, and so.
and this is a pretty big study. They looked at a lot of birds.
There's thousands and thousands of birds. Most of them were mallards. I think 14,000 mallards, something like that.
Yeah.
There's a lot of landings that they were looking at, and they find that almost all of them were north, and within 20 degrees.
Within 20?
20. It was, I don't know, 75, 80% were within 20 degrees of north. A bunch of them were within very close to south, and there was almost nothing either way. So you can imagine if you're going to tell north, it is problematic to tell south. South is the closest to north, and there may be some mix up there, but we can talk a little bit about how animals may tell north from south.
Well, let's.
Okay.
I bet you there's some neurobiology.
So then there's the other one that did the same kind of observational study was these red foxes. And I think the red foxes story is super cool. So it was, what is the angle of attack that they pounce on their prey? So if it's a lighted area and there's not much brush, they pounce in whichever direction the prey is. But if there's a lot of brush or there's snow and you basically can't use vision because you can't see the little mouse, they pounce north-south.
Wherever the mouse is.
They line themselves up so that they will pounce at north, and they line themselves up to pounce at a certain angle. And the combination of that means that they will go a certain distance at that certain angle. And they'll hit, and so, they're trying to go into the snow, they have to go at this prescribed angle. It's as though you were walking around with a laser pointer on your head that's sort of aimed down. And when that matches where the animal is, then you pounce. Because then your pounce, if it's stereotyped, will land on the prey. And that's super cool. And what's interesting is when they did it in the north direction, they were almost always successful. When they did it in the south direction, they were also successful, a little bit less. And when they did it anywhere else in the compass, they didn't get the mouse. So,
Okay.
so this is something that is useful to them, and it's cool. So how do they tell north from south? The idea that I understand.
Can I say one thing?
Yeah.
What's really fun here, she's about to tell us how the mechanisms by which animals can sense north to south. We're going to watch Peggy Mason go right up to the edge of what she knows. Is that fair?
Oh, yeah.
You know what? Here it is. We're about to see the edge of what Peggy can tell us. Please.
How do you know that?
Because with the edge of what you claim to know when you talk to me. How's that?
So the idea is,
About this topic. I mean, there are many other things she knows. I don't mean to.
the idea is that they sense, it's not just that they sense the magnetic field. And when they sense the magnetic field, they're sensing the axis of the magnetic field. So at the surface, the magnetic field is coming off the North Pole and coming down like this, and they're sensing that angle, not the polarity. They don't sense plus minus. And what they do is they sense that angle, and they have another ability called the vestibular sense, which we all have. In fact, almost all animals have, which senses gravity. And what they're calculating somehow is the angle between the Earth's, the angle of the magnetic field and the and gravity. And so if they're facing north, that's an acute angle, and if they're facing south, it's a very wide angle. It's a much wider angle. So that's kind of cool.
That's true. And
Yeah.
so in the bird's little retinas, there's a particular protein.
Well, before we get to our little favorite protein that we're gonna spend a lot of time on, which I'm gonna
Yeah, right. This is where
shove it over to the physicist here.
Okay.
I'll try.
Before we get to that one,
Before we get to that, there's a long history. I remember when I was in school, the favorite idea was to search for a little bit of iron in a bird brain, and they would search deep in the brain, and then there was this idea that there's on the top of the bird beak, there's a collection of ferric oxide, iron oxide, and that was a popular notion.
for how birds sense magnetic north.
Yeah, and so the idea was that it would move with the magnetic field, and then that would move the actual cell, and then there was a mechanoreceptor that sensed the movement of the cell, and then it was basically you're sensing the movement of the compass, and the compass is the little deposit of iron. That seems to have fallen completely out of favor. So people have decided that the cells that have the iron deposits are actually macrophages, not.
A what? So what?
I don't know, they're part of the immune system.
Okay.
Yeah.
Don't worry about it.
Yeah.
Pay no attention to the immune
Pay
system.
no attention. Man behind the curtain.
I understand.
So, yeah, it's part of the immune system, not a sensory cell, not hooked up to the nervous system in any way. So, from what I can tell, and I could be wrong here, but from what I can tell, that idea that we have a little pocket of iron that's moving around like a compass is out of favor. And what is in favor is cytochromes and the lovely
You mean cryptochromes?
cryptochromes, sorry. Thank you. Cryptochromes and the
What's a
lovely.
cryptochrome? What is that? What is that?
Okay, we'll get back to that, but I'm going to shove this over to Maria very soon because the cryptochromes do this through a mechanism that's called quantum entanglement. But cryptochromes are a very cool group of molecules. They were first discovered in plants because they are responsible for DNA repair. Now, if you think about it, why do you need DNA repair? You need DNA repair when there's a lot of energy. Where's there a lot of energy? Where there's a lot of light. So plants have all these proteins that are exposed to a lot of light, a lot of UV light, a lot of high energy light, and it breaks down the DNA. And what you really want is something that's going to fix that DNA. So these DNA repair molecules, and it turns out that this class of DNA repair molecules had a sensitivity to light, to low wavelength light. So that low wavelength has more energy than long wavelength. And so what then became apparent was that this group of molecules, the structure of it evolved over time and is found in bacteria, is found in animals as well as plants. And in animals, it has lost its DNA repair abilities, but it has retained this ability to sense light. And so then everyone sort of threw up their hands, but what has become apparent is that it is responsible, it appears to be responsible for detecting the magnetic sense in most animals. That is the most popular view for, and that it sits in the retina. It's a little bit complicated because even though it doesn't have a DNA repair job anymore, it still has a job as part of our clock. As you may remember, we all have a clock. So even in the absence of any cues, we free run. If we were in constant light or constant darkness, we would free run at about 24 hours, a little over 24 hours a day. Different animals have different periods, but everyone has this rhythm that is close to, not exactly, but close to the sun's or the Earth's rotation. And so to make that internal clock that's always going, you need cryptochrome. So when you delete the cryptochrome, you delete the magnetic sense, but you also delete the clock, and so its functions are, it hasn't been the easiest thing to disentangle, shall we say.
Well, on that, let me just add, before we get it, because this phenomenon apparently occurs because of quantum entanglement. Anybody ever heard of quantum entanglement? Oh,
Good.
anybody?
Yeah, well, if you feel like jumping up here and telling us.
Yeah, oh, I'd love to hear it. Just, I mean, no one really understands. Is it fair to say that no one really understands it?
No one really understands quantum physics, not even.
Okay.
Quantum physics.
Well, so no one, but if you just say it, if you want to offer, it'd be amusing. We'd love to hear what your thoughts, your description, your favorite description of quantum entanglement. She's going, no. Anybody want to offer a?
It'd be a cool experiment to find out.
What do you know all about it? Yes.
When you have a smallest quark at one point in the Earth.
Hang on one second here. We're going to get a mic to you right there. Okay.
Is that when you have two quarks on opposite sides of the Earth, and if you look at one, then the other one says hello, like you're looking at it too?
So yeah, that's a very good description
Anybody else?
of what's going on there. Yeah.
Wait, hang on one second. Sasha's on her way to you.
They say those two particles could be anywhere in the universe, and it happens. They don't know if it goes at the speed of light or beyond the speed of light.
It's one of the Einstein hated that, right?
Yeah, it's hard to explain because we think things must travel at the speed of light, and yet.
And nothing can go faster.
Right. Well, yes, exactly. Nothing can go faster than the speed of light. Yeah.
Any other quantum, just before you get it, anybody else got a quick description or any factoid about quantum entanglement? Okay. What the heck are we talking about?
So what I actually just learned is that quantum entanglement has a role beyond cryptochromes, which I didn't realize.
Yeah,
Being very focused on.
On neuroscience, of course.
there are, ways you could possibly use quantum entanglement to do computing or to transfer information over long distances, but that's a different story. But to talk about quantum entanglement, what exactly is it? So you got a very good description, yeah. How I think about it, okay, so let's imagine two fundamental particles. In my case, I'm going to imagine two electrons. My electrons are entangled. And that means that I cannot describe my electrons individually, but I can describe them together as a pair. And so, if I know information about the state or properties of one of these electrons, I immediately know information about the state or the property of the other electron. And in the same way, if I were to be able to change the properties of one of the electrons, the other one would immediately know about it and have a corresponding change as well. And this happens regardless of if the two particles can see each other. It happens regardless of how far apart they're separated. So yeah.
So it sounds like you're saying, like, if it's you and me, neither of us might have a gender until we figured out what yours was, and then that would tell you what mine was.
You got it. Yeah, exactly. So I could be one of two things. I could be up or down. This is how we talk about electrons. They could have a spin up or spin down. I could be either up or down, and until you measure me, you won't know which one I am. And once you measure me, if I'm up, then we know that you're probably down. Yeah.
That don't make no damn sense, man.
Unless he's up, which is the other way.
Who you measure first, right?
Well, depending on who you measure first will also make a difference on the other. Whatever you measure, there's a corresponding change, and then you can measure. You would immediately know the answer to what the other one would be.
So entanglement, how does something get entangled? Are they like kind of wandering around and having affinity, particles that have an affinity for each other? Hey, you got a good looking electron there, bro.
So generally, you have to have some event that occurs that creates either two electrons at the same. Well, I'm just going to talk about an electron as my fundamental particle that creates two particles at the same time that are somehow linked to each other. Maybe you create them at the same time, or there's an event that forces two particles to be linked to each other in some way, an entangled state.
So now, in the case of our birds, how might that be happening? So we're inside the bird retina, and we're mucking about with our cryptochromes.
Yes.
So some light hits our cryptochrome,
yes,
and somehow
it has to be light of a blue color specifically. So that's an important part about the cryptochrome. Blue light coming into the bird's eye hits the cryptochrome, and it energizes or excites the cryptochrome, and that excites.
Wait, the whole, or just the cryptochrome or the electrons within
it? A particular electron on a molecule that exists within the cryptochrome protein. And this electron is so excited that it jumps from the molecule that it's sitting on to a neighboring molecule. And you spontaneously or instantaneously create something called a free radical pair. So a free radical is a molecule with an unpaired electron. So now you have two molecules, each with an unpaired electron. But because these were created at the same time by the same event, these molecules are now linked quantumly. So
they're entangled!
Quantumly entangled, yes. Yes.
I got it.
So you have to have this one event that occurs at the same time to create these molecules at the same time, to make them entangled.
All right, so I'm sort of with you. We're in the cryptochrome. The light hits. It knocks one of the molecules.
One of the electrons.
Creates a free radical pair.
Yes.
So, but as I understand it, the birds somehow perceive this. How could that be?
Okay, so then there's another step here that happens. So because the molecules are entangled with each other, this also makes them more strongly susceptible to the effects of magnetism, or they feel more strongly the surrounding magnetic field, the Earth's magnetic field. And the magnetic field affects the entanglement states, how the molecules are correlated or linked to each other. And the magnetic field can force the pairs to be entangled for a longer amount of time, or it can force the pairs to change their states in corresponding ways. And that's a result of the magnetic field interacting with these entangled molecules.
Now,
So at that point, you then need to go back to biology, because now
Yes.
there has to be a way in which that sensitivity and that reaction to the magnetic field gets translated into an increased response.
do we have that picture, the famous bird thing? What a bird,
Yeah.
how birds may be seeing this? That's a good little illustration.
Yeah, I think it's...
It's there.
Yeah, that's
yes.
it. So the idea would be that if the magnetic field is hitting your cryptochromes just so, they are conferring to their parent neuron a little extra juice. And so
That's a technical
now,
term.
instead of just seeing what you see it's as though there's a spotlight in the area that is north, or or the whole thing glows only when you're pointing north. Something along those lines is what we think is going on.
So this is the
So it's not going to be there are no photoreceptors that we know of that have only cryptochrome. They have cryptochrome and something else, so that the cryptochrome is only augmenting, facilitating the response to the something else, the other light.
So now, when you say that the entangled electrons are more sensitive to the magnetic field, we just have to accept that, right? Because there's not a why that happens, or is there a why?
Well, you could do some math.
Oh, we have to accept it. Yes,
And
that's right.
you can make some diagrams, and you can show yourself that the effects of the magnetic field force the entangled pairs to react in a certain way. And that reaction, how they react, how long they react, and how long they stay entangled. Because the entanglement doesn't last forever. The entanglement only lasts for something like a thousandth of a second or something like this. It's very quick. And so the magnetic fields can also change how long this happens, change the molecules a little bit in that way. And then that information gets transferred somehow through biology to the bird brain.
But there's a whole lot of photons coming at us too. I mean, it's
Sure,
not, I mean, it's
yeah,
not like
so-
there's like one.
Right, so these things, I mean, I don't know like the frequency, how often these things are happening, but probably all the time, I expect.
Yeah, I mean, but
The
any,
cryptochromes are in the blue, or in the short wavelength. We like to actually say short wavelength rather than blue, because blue is actually only in the brain, not out there. Photons are not blue or red. So the short wavelength cones, which are the least numerous of the cones, and cones are less numerous than rods, so it's a pretty small...
cones and rods.
Cones and rods are two different photoreceptors, that the classic types of photoreceptors that sense, cones sense things in brightish lights. If you can see colors, then you're using your cones. If you can only see dark and light, dark and, different shades of black and white, then you're using your rods. So, at nighttime, you don't know what color the car is because you can't tell color. That's rod vision. So the cryptochromes appear to be in the short wavelength cones. There are actually three different types of cones: short, medium, and long wave cones, and the short wavelength ones are the ones that contain the cryptochromes.
So one of the things that I think is really interesting about, well, first of all, everybody clear? They all got this figured out? Yes, please.
Sure.
Well, hold on, hang on. Wait till Sasha comes to you.
So do I take it from this slide that superimposed over this bird's vision is a heads-up display with a sort of gradient horizon that indicates north? If it's balanced, and off to the left and right is northwest or northeast? Is that what you suspect is going on?
I mean, I think that this is a depiction, and it could be anything close to that, anything in that basic framework. It could be a spot, it could be that the whole field gets brighter, Or it could be that the horizon gets brighter. I don't think that we know the specifics, but and it's probably a little more subtle than that. You can detect really subtle changes perceptually. You will learn to detect subtle changes with enough practice.
And in fact, you wanted to mention?
Yes.
Even
so
humans.
what do you think about? Do you think you have a magnetic sense? Does anyone here think they can tell magnetic north?
Who's got a great sense of direction? Good sense. Okay, great sense.
So
of direction. Okay.
inside, could you tell which? So there's a couple of pieces of evidence or a couple of pieces of data that I'll share with you, and you can make your own decision as to whether you think we have it. First of all, we have one cryptochrome. It's Cry2. There's Cry 1, 2, 3, and 4. We have Cry2. So the first piece of evidence is actually linguistic, and this comes from Leah Borditsky, who's a really, really interesting linguist, and she described a group of people in the South Pacific where they don't use the words left and right, they use the words south, east, west, and north. So they say, well, the person to my east, which I don't know that that's you, but 'cause I don't know which direction that is.
Then it is. You're right.
But you know, the person to my east is so and so, and then you move them around, and now that's the person to their. You know, we could all move together, and now that would be the person to my north or whatever. And so that is very suggestive that people have that kind of a sense. The second piece of data I would share with you is one that was shared with me by a graduate student of mine, Thad Brink. He's now at Medtronic, and he told me about a study, and it turns out Aaron found the study. Thank you, Aaron. By a man named Frank Schumann, and what he did was he made these belts where and there were all these sensors, and wherever you were wherever north was on you, the sensor would be activated and it would buzz your skin. So you wear this belt, and then for two weeks or 3 weeks or whatever, you always are getting buzzed where magnetic north is. At the end of that period, they said, you know, how does it work? And they could detect magnetic north better than chance. They also described it as having a more ordered and larger spatial sense, which I thought was kind of interesting. Anyway, so he did that on a pilot of 4 people, and it worked. And then he thought, oh, well, this would be so useful for blind people. So he got a person who had been blind from birth, and he tried it, and it didn't work. And his conclusion was, oh, I'm wrong. It doesn't work but my conclusion is, oh, he's right, because this person doesn't have cryptochromes. And that's why it didn't work.
Okay.
Now, you know, there are a lot of ways to follow that up, and 5 people, 4 of whom are sighted and 1 of whom is blind, is not enough of anything to tell us something, but I think it's a very intriguing idea.
Dr. Weber, as I understand it, this whole a lot of this quantum stuff, particularly entanglement, shouldn't happen in biology.
Well, I don't know if we would say it shouldn't happen. We find that it does, and that's weird, I guess.
Okay, that's what I meant.
I've learned over many years that you should never say that something shouldn't happen in nature or in space, because it probably will happen, and then you have to find a reason to explain it. But so I was thinking about this a little bit, and so when we see a bird or whatever, we look at a brain of some animal, we're seeing it macroscopically. We see the whole thing. We see it as like the squishy, wet, kind of warm mess. But the particles do not see it that way, right? The particles are these little tiny things, and on their level, there's a lot of space between individuals, and they're on a microscopic quantum scale. And so they're not feeling the wet, squishy stuff. They're seeing a lot of empty space and a lot of things zipping around. And so their world is a little bit different than the world that we see.
But they're, at the same time, they're also feeling this very macro
Right.
field
So they
that
can,
is coming from the North Pole that is way, way bigger than my brain or your brain or the squirrel brain or, so they're sort of got a foot in each
exactly.
in each world.
So inside a living thing, you cannot, isolate the quantum effects from the environment.
Yeah.
Right? But we can in a lab, kind of. And so it's hard for us to try to replicate some of these things happening in living systems on the quantum level in the lab. And I guess part of it's because we're missing out on something important about the macro scale, perhaps.
Well, there's also the quantum effects, what do they call it, decohere, that the effects, what am I talking about?
Yeah, so if you say that entanglement decoheres, I guess, that means that the entanglement state breaks. So particles don't stay entangled for forever. They just have a short time period over which they're entangled. So in the particular case of within the cryptochrome, they can stay entangled for maybe up to 1,000th of a second. And in the lab, you can achieve different time scales, but I don't know, the exact numbers on that.
So can I say that, so when we talk about quantum, as I understand it, we mean it as opposed to classical mechanics, the physics.
Sure,
So
yeah.
what's the difference between classical physics and quantum physics?
So I guess one example of classical physics that I like, the difference between classical and quantum physics, comes from something called the double slit experiment.
Wait, how many people have heard of the double slit experiment?
Some of you.
Okay.
Okay. So in the double slit experiment, you have two empty slits here, and then behind that you have a screen.
Like there's a wall with two slits cut in it.
Yeah, and then behind that you have a screen, and then on one side you have let's say a laser shooting photons at these double slits. But first let's start by the classical representation. Instead of shooting photons are like individual packets of light. That's one way you could think about a photon. Instead of shooting packets of light at these double slits, let's shoot a ping pong ball at these double slits.
At the wall with the two slits cut in it.
Yes.
Right.
So if you shoot a ping pong ball, the ping pong ball only has one choice, one way to go. It will go through one particular slit or the other, whichever way I'm pointing it.
Or bang against the wall.
Or bang against the wall, right. If it finds its trajectory is aimed for the point where there's no empty slit there.
Right.
So that's a classical description.
And then leave a mark on the screen behind.
It would leave a mark on the screen behind it only if its trajectory was perfectly aligned to pass through that empty slit and hit the wall behind. But
Are we all clear on that, what she's talking about?
so imagine
Okay.
ping pong balls, throwing
Yeah,
them,
okay.
and only a few of them get through the hole that's open. All right. But
And then make it sort of a sloppy cylinder, two sloppy cylinders on the screen behind.
maybe imagine like you're paintballing or something.
Yeah.
Yeah. And your paintball makes a splat on the wall. But now, instead of these ping pong balls, we have photons, these packets of light. But the weird thing about quantum mechanics is that the photon actually can take both paths at the
Can
same time.
I say something? Just because as opposed to the ping pong balls, if you had like water going through, like if you just like slashed a bunch of water going through, when the water would, the waves of water would go through both slits
Yes.
and form an interference pattern on the other side of the
Yes,
slit.
sure.
And
So
it's-
so imagine you were like in a lake and you are skipping stones. You drop a stone in there and you see ripples appear on the surface. Yeah, you create these interference
So
patterns.
the wave would go through both slits and
Yeah.
have an interference pattern on the other side. Okay.
Yes. So now in the quantum mechanics world, we have a photon, and the photon actually can go through both slits. It can choose both paths to go through the slit at the same time. So it can choose both paths, go through, and then on the wall behind, we won't see just one spot where it came through. We'll see the sort of ripple pattern of interference. Because it can,
But I know what to do. You just set up a camera to see which slit it went through, and Bob's your uncle.
no. It turns out that quantum mechanics things don't like you to look at them, actually. So so one thing you could try is to put a detector on behind one of those empty slits there to try to catch one of the photons. But whenever you do that, you don't create this interference pattern anymore. So.
You mean if
Oh,
you
sorry.
look, it decides which one, it decides to go through one slit or another, depending on whether or not you're looking at it?
Yeah, if you force it to, in a sense, you're forcing it to make a choice. So it has to choose. It can't be both at
You're
once
forcing
anymore.
the photon to make a choice?
You force it to have to take one path instead of both.
This makes sense? We all good here? You all good? You understand it all?
Well, I'm a biologist.
So, anybody have a question for her about this, or it makes no sense to me? Yes, sir. Wait, there's Sasha right there.
In the broader sense, do we make our own reality by looking at something?
Well,
Yeah.
I mean, in a neurobiological perspective, yes.
What?
You only, the reality is whatever you make it in your brain. There is no, for example, there is no color out there. The dress has no color. Your brain assigns a color to it.
Which makes no sense to anybody.
Wait, hang on 1 second.
Which makes no sense what?
To other people.
It makes no sense to other people.
At the same moment, if you make yourself, then other people will not see the same way as you.
There's
Oh, if everything is inside your head.
There's zero evidence that two people see the same thing. That two people have the same experiences. There's a great essay by Thomas Nagel called "How It Feels to Be a Bat." And he starts out by trying to imagine what it feels like to be a bat, and you know what you realize after a moment is that you can't feel what it is to be another different person. And I would even go farther from a neurobiological perspective. I don't think you can tell how it felt to be you yesterday.
So at that point, are you at the Hindu thing of nothing is real and it's all Maya? It's all an illusion?
I don't know anything about Hinduism, but the reality that you create is not an accurate representation of the physical world. So we are not tape recorders or cameras. What we create is actually really good for one thing: survival. So it's really good for evolution. It's good enough to get us to today. And it's been good enough for all the different extant animal species to get them to today. But it's not an accurate representation.
Well, can I say that, because part of it is that the forces fool our senses. Was there business about Eddington's, are there Eddington's two tables?
I'm not familiar with this.
About the two tables, the table of nature and the table of physics. The table of nature is solid and hard.
Oh.
Right.
And the table of physics. Well, continue with your story, and then.
Well, the table of physics, Eddington said the table of physics is solid and hard,
Yeah.
and then if I burn it, it's turned into something different. But the table of physics is a cloud.
Oh, sure.
And it's mostly empty space. And if I burn it, it doesn't change. It's still the same thing.
99.999 or more % of us is empty space. Right. So
Yeah, see, this is what I'm saying. Yeah.
we feel solid. This is solid, but there's so much empty space there.
So why does it feel? Okay, well, this goes off. But to your point about we make our own realities and our senses fool us. These electromagnetic things make it seem solid because we can't go through it.
Sure. I had a professor in college who would always, a philosophy professor, who would always talk about that what is it like to be a bat? What are you like? And then he would also talk about, how do you know you're not a brain in a jar?
So brain in a vat is another really fun fantasy or conundrum to think about. How would you feel if you were a brain in a vat? What would be different from how you are as a person? Yeah.
So you guys are really great, and I don't want to keep our guests too long because they have to get back to Hyde Park. But one of the things that has really fascinated me about this topic since my dear beloved Peggy brought it up is this notion of quantum biology. Because as I understand biology, it generally thinks about the world in a very classical kind of way. When we talk about the electron transport chain in mitochondria, which is how we make the magical firecrackers, we describe the electrons in terms of being discrete particles. And they have these discrete paths, and they're passed along this electron chain. But we know
That's how we teach it more than it.
Well,
because even in biology, I mean, we're not physicists, but even in biology, everything is a probability.
Oh.
Everything's a probability. So, the channel opens or the channel closes. What that means is now there's a chance the channel will open. The chance that the channel will open has shifted from X% to Y%.
Now, when you say probability, that's what you're talking about in quantum mechanics, right? That it's all probable. That they're. What does it mean about probability in quantum mechanics?
Quantum mechanics is built a lot on probabilities. Like, for instance, when we were talking about the photon possibly being able to go through like sort of both paths at the same time, we can describe photons through a terminology called the superposition, and these photons have a particular path, a many number of infinite kind of paths that they can choose, and they all have some probability associated with the fact that they could choose one path or the other. So all of these things have sort of probabilistic effects, especially at quantum levels attached with them. So the particle could be in a million different places at one time, and you could describe it by adding up a bunch of different probabilities for different possibilities of where it could be.
Is that what you're saying? That's
absolutely true in biology too. It's a little easier to think about it as the channel opens. But all that means is there's a population, and now the probability has increased for X percentage of the population that are responsive.
So you don't tell your students that because that would make their brains explode?
It depends on which student it is and what the course is.
Yeah.
But certainly the students learn that when they learn cellular sort of neurophysiology, yeah.
Questions, comments, weirdnesses, things that seem strange that you'd love a little more light, a few more photons shed upon. Well, yes.
You were talking about the shifting the magnetic field, right? So if the birds have the senses, does that mean if the pole will change their location, for example, it would be in the center of Canada, for example, and the bird would land supposedly come, let's put it, 200 miles before the center of that magnetic field of the true north. So does it mean if that's shifted, it may land in Illinois, for example, instead, if you have that senses of magnetic field?
So
what is going to happen?
I think so what you're asking is, what if the magnetic sense is used for orientation, for essentially for migration?
Yes.
If it's used for hunting or for landing, it doesn't really matter where you are, as long as everyone's on the same path. And so that wouldn't make a difference. But if you're trying to find home or last year's home, then it could conceivably make a difference. And I have no idea how the animals adjust for that, or if they do. I just don't know. And and every once in a while, we forgot to talk about this, but I go down various rabbit holes, and I'm not really down the quantum rabbit hole because it's way too complicated for me. But the magnetic north rabbit hole is very interesting, and occasionally it decides to flip.
Yes.
And that's cool. So when has that happened in evolution? Because that's not that infrequent.
So the last time the Earth's poles flipped was, I think, 780,000 years ago,
Yeah,
not
so
quite a million
nothing.
years ago.
Nothing.
But the Earth's, when it flips its magnetic field, is quite chaotic and it isn't predictable. So it's hard for us to say when it might flip again, and if the fact that the pole is wandering right now, whether or not that means a flip is coming in the future, I don't know. I've been seeing a lot of articles about like, oh, the wandering pole means that the Earth is going to flip its poles, or that maybe in some places the magnetic field strength is decreasing. That happens over time as well. It's hard to say exactly when this polarity change might happen.
And it's also, I haven't gotten a clear answer as to how long it takes to flip.
Yeah, that is a hard question to answer. I think it's not clear. I think you can get some information about this by looking at like rock cores and ice cores, because the rocks, the particles in the rock will line up with the direction that the Earth's magnetic field is pointing. Also, particles of ice will do the same thing. So you can sort of see a layer like you can like sediment and rocks, and it tells you some information about that. But I don't know if we can tell or how we can tell how fast it happens.
Right.
Yeah.
And on different planets within our solar system, the orientation of magnetic north, because the Earth's magnetic north is not perpendicular to our orbit,
But it's close.
but on different planets and other.
Yeah, so if we want to talk about, this is just, it's a cool thing. So here's our Earth. The Earth is tilted at about 23 degrees from vertical, and so it rotates around that way. And so then the red axis here is the axis of the magnetic field. And so you see on Earth, it's offset by about 11 degrees, that number here. On Saturn, the rotational axis and the magnetic axis align very well. And Jupiter, not offset by very much, but look at Uranus. Uranus is actually tilted on its side and rotating on its side, but its magnetic polarity is totally off with respect to its axis, and Neptune as well. So it's a
So Uranus is rotating with the axis of rotation pointing at the sun, like it's a spoke on a wheel.
Mm-hmm.
Yeah, which I thought was super
it's
cool.
weird, yeah.
And on that very weird note, how about we thank our wonderful guest?
One last question.
We have another question. Sorry about that. Yes, go ahead.
Yes, I always see discussions of what point in the northern territories the magnetic pole for north is, but I never see one on where it is on the other side of the globe. Is there not a corresponding point that wanders around down there too? And if so, where is it and why don't we hear about it?
On the South Pole?
Mm-hmm.
Yeah, well, I'll just show, I do have another figure here.
Just happens to have a slide.
So there are a bunch of different ways you can map the Earth's magnetic field. And so in red here is sort of like a north polarity, like a pole of a magnet, and then in blue is the south polarity. And so in the northern hemisphere, the magnetic north is kind of somewhere up around here. It's actually not plotted on this map because it stops at 70 degrees. But the South Pole is actually somewhere right around here, the South Magnetic Pole, sort of just off of Antarctica a little bit. And it can move, and it does move a little bit over time, but I guess that's talked about less in the news, maybe. It's less apparent to all of us.
Less.
At the moment,
Okay.
maybe. But in the past history, maybe not. It's just in the current stage, the current time that we're in now, it's the North Pole is wandering maybe a little bit more than the South Pole, although the South Pole still meanders as well.
So now I'm really confused.
Yeah, you got it.
As if I wasn't before. But I just assumed, whenever I've heard about this wandering North Pole thing, magnetic pole, and when you talked about it, I've always assumed that at the other pole, it's doing the equal and opposite thing.
Nope.
So this stuff isn't on an axis, like the magnetic north and south are not opposite each other?
Not exactly opposite,
Oh,
no.
God. Okay.
No. No, it would be like very convenient and easy if it were, right? No, and this is a fact of the fact that we have in the interior, the thing that's creating our Earth's magnetic field is this, again, this rotating molten liquid interior, metallic interior, and it rotates in different ways in different parts, and some parts of it have these big upwellings and some parts are moving a little bit more slowly, and all of these things together mean that the system isn't going to be exactly symmetrical around the equator. In fact, our sun has magnetic asymmetries in the northern and southern hemispheres that we see, and so our Earth does the same thing. Mm-hmm.
Oh, Kristen? Right here, right there?
No, Anna's got a
Oh,
question.
yeah, sorry.
A question and a comment. So the question about the northern hemisphere, isn't the ring of fire, the volcano thing, more in the northern hemisphere? And would that, with volcanoes erupting, would that have an influence on the movement of the North Pole?
So
Magnetic
that
North Pole?
is beyond my area of expertise to really say much about. I don't know much about the processes that happen in the upper crust or in the Earth's sort of upper layers. So I'm afraid I can't really say much, and especially I can't say much about how that might impact the magnetic field. So I'm sorry, I can't speak to that.
Do you know anything about that?
Her guesses sounds
Wait,
good to me.
hang on. This is Bill Higgins, who's a physicist at Fermilab, and a good buddy of mine, Mr. Beam Jockey on Twitter.
You want to talk to somebody that really knows physics and crustal plates and that kind of stuff, but volcanoes and earthquakes are a phenomenon of the top 100 miles of the Earth's crust, and that's way above the kind of phenomena that you've been talking about here. I wanted to mention something about the offset of the magnetic pole, or the magnetic field is not centered at the center of the Earth, which you were speaking of just a minute ago. The one consequence of that is it's a little closer to the surface on one side than on the other side. And one of the things that follows the magnetic field is the donut of radiation particles circling the Earth, the Van Allen radiation belts. And so because of this magnetic asymmetry, there is a thing called the South Atlantic anomaly, where in the radiation belt is closest to the Earth over the South Atlantic. And when satellites circling somewhere near the equator, or the first 20 or 30 degrees above or below the equator, when those kind of satellites come through over the South Atlantic, that's when they see the most radiation in the low orbit. Mostly they're below, the satellites I'm talking about are below the orbit, below the bottom of the radiation belts, but they skirt them around the South Atlantic, and if your spacecraft is taking scientific measurements, or maybe the Hubble telescope is trying to take a picture or something like that, you kind of got to watch out for that when you're operating the spacecraft, because it's one of the many boogeymen that could give your spacecraft trouble.
Thank you, Bill. And Kristen?
My question is completely unrelated to, well, mostly unrelated. My brain got sidetracked at the very beginning of the talk. We were talking about something having to do with magnetism residing in the immune system, or immune cells.
No, these deposits of iron that are on a bird's beak, they are they were thought to be the sensor of magnetic north, but to do that they would have to be sensory cells that actually made their way somehow to the nervous system, and it turns out that they're actually immune cells. So why do they have iron? I have no idea.
Is that true in humans also?
No. This is a thing on the little beak,
just
of
on the beak
of the bird. Yeah, it's a very special structure.
We have cryptochromes in our retinas, but no iron in our beaks. Doggone it! Wait, one more. And I see.
How about the iron in our blood?
How about what?
The iron in our blood, hemoglobin.
Yeah, it has to be, to sense an orientation, it has to be fixed. So there's also an inner ear structure in, what is this in? It's called the canal of the ampullae of Lorenzini. And it's in sharks and stingrays. And it senses electric fields, and because it senses electric fields, it can sense, by Faraday's law, it can also sense a magnetic field. And so that has, that exists in them, and I saw a speculation that could also be a sensor in that human or vertebrate semicircular canals could do a similar thing. I have no idea if that has any reality or not.
Okay.
Yeah.
So this is part of my comment. It is an eighth nerve-derived organ, the ampulla of Lorenzini. My comment was going to be that in birds, but not in mammals and other animals, their hair cells, their detectors of gravity, have in their cuticular plate, the top part, an iron-rich organelle. And it's thought that perhaps can detect magnetic fields and possibly have to do with migrating birds. I don't know if, it hasn't been described in like whales, which migrate for long distance, but definitely in birds.
So in birds, but not in mammals.
Or fish or frogs or anything.
And
Birds.
is it all the hair cells, or is it the hair cells of the sacculus, or?
Pretty much all the hair cells. I have a reference from it.
Yeah, cool.
That would be Dr. Anna Lisakowski, who's the president of the Chicago chapter of the Society for Neuroscience, Chicago SFN, ChicagoSFN.org.
And a great vestibular neuroscientist.
And a great vestibular neuroscientist and a great gum manufacturer. She makes gum.
Okay, I have a question for Maria. It's just rolling back when you were describing the experiment when photon supposedly is forced to choose when we put the detector. Is it the illustration of Heisenberg principle?
The Heisenberg,
Because you're changing the momentum when you start detecting.
so the uncertainty principle is the fact that you can't know how fast something is moving and its position at the same time. So I don't really know how this relates, I guess. Maybe someone else in the room might be able to speak.
Well, to the extent that
more
the
to that,
act of observing changes the phenomenon.
Yeah, it's certainly that the act of observing changes, but the Heisenberg uncertainty principle is the fact that you can't know a position and a speed at the same time. So.
Also, because one of the weird things about this particular two-slit thing, that the measurement occurs after it has already gone through the slits. So that in theory, you could still know as much as you needed to know about its position or its velocity. But what's weird about it is that the observation after its choice has been made changes. That the consequences of the choice change after the choice has been made, and that's what's. All right. Well, thank you guys so much. But so let me just say that you can, Dr. Weber, you're on Twitter at
Solaris Maria. Solaris because I'm a solar physicist. So Solaris Maria.
And you are on Twitter as
Neuromook.
Neuromook. And her blog is
TheBrainIsSoCool.com.
You got a blog? No, you're on Instagram though. You're on Instagram.
Oh, I'm sorry, yeah. On Instagram, I'm Dr. Solaris Maria.
And we're the Chicago Brain Buddies, and we are C2ST.org is your source for public information about sciences across the spectrum of scientific disciplines. And we thank you guys all very much. Thank our guests. And you all, thank you very much. It's been lots of fun.